This conference will now be recorded.
We are going to discuss today Newton's forward interpolation formula. I am audible? Audible?
Yes, sir.
Okay. So Newton's forward formula, or we can say Newton's forward difference formula. So, pardon? Newton's screen is smaller, don't worry. Newton's forward difference interpolation formula. So either we say it Newton's forward interpolation formula or Newton's forward difference interpolation formula. The difference word is hidden, and without difference we cannot talk about the Newton forward interpolation formula because the main concept is the difference. So far we have seen the concept of the interpolation, various operators in this Newton in case of interpolation. So if you revisit your concept of the interpolation, what is interpolation? We have seen this is an estimation of the value of the function. This is an estimation of the value of the function corresponding any value of the independent independent variable or the arguments. This was the concept of the interpolation. And similarly, what was the concept of the extrapolation? Extrapolation was the method to estimate the value of the function for any value of the independent variable or arguments outside the range, that is taken outside the range. In case of interpolation, the value is taken, value of the argument is taken within the range or inside the range. Thereafter, we have seen several difference operators. What are the main difference operators? Let us revisit once more. That difference operator is, the first one was the forward difference operator. Second one was the backward difference operator. Third one was the shift operator. Fourth one was the central difference operator. Fifth was the averaging operator, and sixth was the differential operators. So these were the important and useful operators which we have already gone through, and we have come across the deep and long discussion about them. Now we are going to discuss the Newton's forward interpolation formula. In this formula, what happens? You are hearing me, Rajkumar?
Yes, sir.
Okay, so let us consider a function. You look at this screen, y is equal to fx be a function having n plus 1 data set, xi, yi. I is ranging from 0, 1, 2, 3 up to m. Let phi x be, this is the very simple nature of the simple type of the function we have chosen here, a general form of function. But corresponding to this function, we have generated a data set. That data set is n plus 1, and its value is ranging from 0 to n, and therefore this is n plus 1. Now let us consider a polynomial. Now the role of the polynomial has started. Let phi x be a polynomial of nth degree which approximates and represents the function ys. I have already discussed time and again that this polynomial, this function given or considered can be approximated with the help of the polynomial, and perhaps this is the biggest contribution of the interpolation in the field of the numerical analysis. So what we do further, after this choosing the polynomial which is going to approximate the given function, we can simply write fx is equal to 5x plus error term. This is the simple concept of the interpolation. When we are going to approximate any function with the help of the polynomial, then naturally approximation produces the error, and that error we have already discussed whole one chapter about the error, types of the error, the regions of the error, how to compute the errors, the relative errors, the absolute errors, all kind of errors we have already discussed. Now this error term is created due to the approximation. These are the usual simple ideas regarding the approximation. Now what we are going to do, now this polynomial phi x is equal to a naught plus a1x plus a2x square plus anx to the power n, and condition is this, that an is not equal to 0. Why this an is not equal to 0? Because this an decides, if you put here 0, this goes to 0, and the previous term will decide the degree of the polynomial. Means then suppose here is the an minus 1, an minus 1 you say, and here x. Here xn minus 1, here xn minus 1. Then this is what? If you put an is equal to 0 somehow, however, you can consider this is equal to 0, then this whole term will be 0, and degree of the polynomial will be this highest power of the x. Highest power of the x is what? Highest power of the x is here n minus 1, and therefore the polynomial's degree will change. And therefore, here one condition is made about this an, that this is not equal to 0, so that the degree of the polynomial is not affected in any way. So this, if you look at this polynomial, this is a very popular form of the polynomial, that is a power series form. If you remember the term power series form, power series is a very important and useful topic in the field of real analysis, in the subject of real analysis, or you can say the applied real analysis. So what happens here, this one is popular, and if you remember the discussion which has taken place in various literatures while studying and going through the concept of the power series, that the Taylor one Taylor theorem or the Taylor expansion we have already discussed. The Taylor has suggested the shifted power form of the same polynomial. One polynomial I have told you, I have shown and discussed about the nature of this polynomial. This is the simplest, very popular form of the polynomial in the form of power series. The Taylor has suggested, if you want to consult this topic, and I would suggest that you must consult this power series so that you can have the different form of the polynomials. The Taylor expansion has suggested the same polynomial can be written, can be expressed. This is given with proof. A naught plus a1x minus x naught a2 x minus x1 is x naught square, this and this plus, and this is the last term is an, last term is an is equal to an multiplied by x minus x naught to the power n. So this is for single, this is for one, this is for n, this is for 1, this is for 2 x minus x naught. So for so on, here you can put here an minus 1 x to the x minus x n minus 1 to the power n minus 1 degree n. This is what? This is the shifted power form polynomial suggested by the Taylor. So this polynomial we are not going, since this value x naught is a constant value, if we put here, so substitute some value of the x naught given, then simply this x will remain. Similarly, x minus this, if you open the bracket, you will find x square is square of this, and then 2x naught and x. Substitute the value, then you will find the x square here and x to the power 1. So if you want to add here, so you can do it. Similarly, this polynomial is nothing but the degree n, and after substituting the constant values, constant values, constant value is this one. This polynomial remains almost the same as we have seen above. Now also the simpler polynomial is written in Newton's form, degree polynomial and degree polynomial, and how it is written, you look at it. Phi x is equal to phi x is equal to a naught plus a1 x minus x naught, a2 x minus x1, and a3 x minus x naught, x minus x1, x minus 2. You look at it. So in case of a1 x minus x naught, and in case of a2, we have introduced one more constant x1. There are two terms. Similarly, the three terms, three factors are multiplied here, and similarly here it started from 0, so n minus 1. Again here is n factors. So what you are getting here, the x you are getting here, again you are getting x square if you multiply here, and constants values and some power x. So simplify, if you ultimately simplify, this will also remain degree n. There is not any problem in the degree. Degree is n. Degree n. So in case of degree n, now this polynomial, another form of polynomial suggested by the Newton, this polynomial has been used in Newton's Newton's forward interpolation formula. So B and C, I have shown you the two different polynomials in place of the simple polynomial, and these things are these things are available under the topic power series in the real analysis. So I have revisited and I have made a revision of your topic power series. So let phi xi is equal to yi. I is ranging 0, 1, 2 up to n. Phi xi is equal to yi. What does it mean? Phi xi is equal to yi means this phi xi is approximating each and every value of the function. Why? Because we have already considered that this is the approximating polynomial. This is the approximating polynomial. In case of the interpolation, if you remember, when we suggest and we replace the complicated function by a simpler polynomial, then polynomial was known as approximating polynomial, and method was known as a polynomial interpolation. So here this is a approximating, this is an approximating polynomial, and approximating what? This is approximating the value of y. So similarly, this will approximate the value of y the as per the nature considered for the approximation of the function. Now question arises how to evaluate or how to compute the values of a0, a1, a2 and an in C. So C is what? C is this one. This polynomial we have preferred to approximate or to approximate the function fx. Y is equal to fx is a function which is needed to be approximated by a polynomial. So we are given three important polynomial. The first one I have shown you, the simpler form of the power series. Second one I have shown you, suggested by the Taylor expansion. Third, C is has been suggested by the Newton. So Newton has taken his, you can say, his polynomial for the development of the interpolation forward formula. So how we are going to, we are substituting the value x is equal to x naught in C. When we are substituting the value of x is equal to x naught, this is a value of the x. X is the argument, and the first initial value of the argument is going to start from the x naught. So x naught is substituted in C. You look at here, I am going to show you what is C. What is C? Where is C? X is equal to x naught is substituted in C. So this becomes what? This becomes the phi x naught. This becomes phi x naught, and here a naught will remain same, and here we put x naught. Here we put x naught. So x naught minus x naught is equal to 0. So only this term here, x minus x naught, here is also x naught, here is also x naught. So x naught minus this is 0. Again this is 0, again this 0. So all terms, this term will be 0, this term will be 0, so forth, so on, this term will be 0, this term will be 0. So what is remaining, I am going to show you what is remaining here. X, after substituting x is equal to x naught, we are going to have phi x naught. This is phi x naught, and a naught, other things are 0. So phi x naught, as per the, since it is approximating, and this I have already shown you this part, I am using this part. So phi x naught is equal to y naught here. So the same value we have chosen here. Phi x naught is equal to a naught, and phi x naught is what? Phi x naught is a y naught. Y naught is equal to a naught, so a naught is shifted in the left hand side, so a naught is equal to y. So a value of the a naught is computed here. The first constant is computed here. Now we come to the second constant. For computing and evaluating the value of the a1, that is the second constant, we substitute x is equal to x1. So when we put x is equal to x1, this becomes the x1. This is a naught. This is a1, x1 minus x naught. X1 minus x naught. So x value is x naught, x1 and x naught, and every terms, because x1 minus here will come x1, x1 minus x1, x1 minus x1, x1 minus x1. So x1 minus x1, so this will again a 0. So similarly all terms will be 0. So here what is remaining, the a naught is here, a1 is here, and this difference is here. So y1 is equal to y naught a1 x1 minus x2, and this is transferred in the left hand side, and the right hand side is available as a1 x1 minus x naught, and a1 is further simplified, so y1 minus y naught upon x1 minus x2. By the difference nature of the difference operator, definition of the difference operator, This is the delta y. First difference. And this difference is what? This is a space or length that is known as h. So A1 has been obtained, A0 has been obtained. Similarly, x is equal to x2 is substituted in C. What you get, this value you get, this value you get, this value you get, remaining things are zero. And after simplifying and substituting the value of A0 and A1, here we put the value of A0 and A1 in the above expression. This becomes this way, and ultimately we substitute the value where, for example, 2h. You look at here 2h. y1 minus y0, y2 minus y0. 2h is what? You just look here, otherwise x2 minus x1 is 2h. x2 minus x0 is 2h, means x2 minus x1 minus x0. There are two steps, then we reach x, and therefore this space is 2h. Okay, and this is x1 minus x0. This is x1 minus, this is here. Here is a2, and x2 minus x1 is h. This is 2h square is here. 2h square is here. 1h goes from here, h. x2 minus x1 is h here, and x2 minus no, there is some here some problem, because okay, anyway, you can check it in the writing. Ultimately, I'm showing you what we are going to have in the similar way. A2 is equal to y2 minus 2y. This is minus 2y1 plus y0 upon 2h square. So this is a very popular formula, if you remember, and this popular formula gives, in case of difference, we have seen difference operator. This is delta square y0 and factorial 2h square. This is the value of A2. Similarly, we can obtain the value of A3. This is the value of A3 and an minus 1, the lambda delta n minus 1 y0 n minus 1 factorial s to the power n minus 1, and ultimately we obtain the value of an. We obtain the value of an delta to the power n y0 and factorial n and s to the power n. So here, upon substituting these values, we have obtained all the constants. You look at here. All constants are obtained and computed and well received. Then you look at the polynomial. C becomes C polynomials means A, B, C. This was the polynomial. Y not, A not in place of A not, be substituted. Y not in place of A2, be substituted this part. In place of A3, be substituted this part. This remains as it is. This remains as it is. X1 minus x minus x naught, x minus x naught, x minus x1. This remains as it is. And in place of an, this is substituted this value, and this value remains as it is. X up to x minus x minus. Okay, now this is one very important stage we have crossed, and we have arrived at after evaluating the value of all the possible constants given involved in the polynomial. So let us introduce, you look at here, this is very interesting. In your book, it is simply written and left without discussion because it has a very good background in our mathematical discussion in real analysis or in applied. You will also find this concept in statistics, this concept in numerical analysis. Everywhere in the applied sciences, you will find this concept of introducing a new variable. There is a trend of introducing a new variable. We are going to introduce a new variable, u. Why we are going to introduce new variable? What is purpose of introducing the new variable? And you will find that the Newton's forward interpolation formula has been expressed and been written in terms of this new variable, not in terms of x, not in terms of the old variable. So how this has been introduced in this one, you look at the u is introduced, u is equal to x minus x is the variable, argument, independent variable, and h is the here h. Here h, you can put any value, but per chance here h is a difference, but here h is, this is different. You can put this new value. For example, this concept is known as change of original scale. Changing original scale. So far, whatever we have discussed, what discussed with the variable x, what was the origin and what was the scale? There are two things. One is the origin. One is the origin. One is the origin and another is scale. Another is scale. I give you one example that, for example, this, suppose this is x, the old variable, and this x is written as 200, then it is 400, the values are written, then 600, then 800, then 1000. This is x. Okay. Here, I mean origin is 0. Okay, first I explain another one. The new variable is u. U is defined as x minus x naught upon scale. H is scale and this is what x naught is origin and h is scale. Suppose x naught is 600. We are taking the mean here. X naught is taken as a, for the convenience, we have taken the 600 as a mean. So what will be 200 as for the new variable will be what? This 200 is the x, and that is the x, minus 600, that is the origin, x naught, and upon h. Suppose eh is equal to here, eh is a scale, eh is equal to suppose 100. we are changing the scale. So if you divide by 100, what value we get? That is equal to 200 minus 600 minus 400 divided by 4, that is minus 4. And similarly, if you do the same thing, minus of 600 and divide by 100, you will get what? You will get minus 2. Similarly, in case of 6, what you will get? By the same formula, you get 0. In case of 8, what you will get? You will get plus 2. And in 1000, what you will get? You will get 4. So this is the new variable. New variable means 200 has become minus 4 and 400 become minus 2 and 600 has become 0 and 800 has become 2 and the 1000 has become 4. So in this very case, you have seen after changing the origin as a scale, you will say here is the scale is 100, here is the origin 600, but what is here? What is origin here? What is origin here? What is scale here? In this old variable, in x, here origin is 0 and h is 1. So 0 has been changed to 600, this has been changed to 600 and 1 has been changed to 100. So by introducing the origin, new origin and scale and changing the origin, we have changed the origin, we have changed the scale, we get a new variable. And that why we do this? Because of the because of the ease of handling the data, because of ease of handling the data, because of convenience of handling the data. So you can look at data has become so simplified. So similarly, we have changed here. You look at here, u is equal to x minus x naught and divided by h. So UH, we have obtained value of UH, x minus x naught and x naught, x minus x naught is equal to UH. So next, x minus x1, you look at here, x minus x naught is the first way of writing in terms of the u. Here, you look at here, this x minus x naught is equal to UH. Similarly, the x minus x1 is written x minus x naught minus of x1 minus x naught, you just open it, elaborate it, minus x naught minus x1. So we are interested in x minus x1, this minus x1 and this plus this minus x naught and this plus x naught will cancel each other. When we take the common from here, UH minus H, then H U minus 1. And you can say x minus x naught is equal to u minus 1 h. Similarly, by the same process, we can get x minus x2 by writing this one. So x minus x2 is here. Purposely we have got it, and this is the perhaps the purpose. But here the repurpose is what? Introducing the x1 again, so minus x1, here is the plus x1, this will be eliminated. So we get what? U minus 1 h. Ultimately you can say u minus 2 into h. What is this? X minus x2. So you just look here, and last term in C. Last term in C is what? This is the last term in C. If you look at the polynomial, then x minus x naught is equal to u minus 1 n minus 1 into h, u minus n minus 1 h. So this one is all values have been changed in terms of u. Now what is to be done more? Upon putting these values of x minus x naught, x minus x1, so forth, so on, in what? In main polynomial, that is the C. So C, if we substitute this C, in C these values, you please look here, you will find the interesting formula. U into delta y naught, u minus u1 upon factorial 2, and delta square y naught. Similarly, the third term, fourth term, and the last term is this one, u into u minus 1, u minus 2, u minus n minus 1, delta square, delta n y naught. And last is here, denominator is factorial a. This is a interpolation formula. So this formula is called Newton's forward interpolation formula, or Newton's forward difference interpolation formula. This formula is very useful in what? What are the applications of this formula? What we are going to do by this formula? This formula every student has to remember and has to commit it to the memory, just like the routine information we have in our mind, so that in the examination you can apply this formula. So today you just memorize this formula, because tomorrow we are going to handle the numerical, discuss the numerical on the basis of this formula. So this is used, what is application? This is used to interpolate the value of function y lying in the beginning of the tabulated data set. This is a very restricted application. This application has been restricted. Why? We will discuss during the numerical that this condition is very important. You please take a note of this condition, be mindful of this condition, value of function y lying in the beginning of the tabulated data. If you are given the tabulated data, so this formula would be suggested to apply in the beginning of the tabulated, not in the middle, not after the middle. So it is only to apply in the beginning of the tabulated data. So this is very important. Take a note of this word, this term, and we will explain numerically also on the next term. Second one is what? This can also extrapolate the value of the function y. I mean, interpolation is also applied through this formula, and extrapolation is also applied through this formula. But in both of the cases, there is a condition, and that condition is what? But little bit backward of initial value of y, say y naught. This is here very restricted condition. There, this is a constraint. This little bit backward. Suppose you are beginning from y naught, your value, tabulated value corresponding to x naught, this one, Then so forth so on is here, so forth so on is here. So here is the yn, here is the yn, here is the xn. It will make the extrapolation not after the yn, outside the range. What is the extrapolation? Extrapolation is an estimation of the value of function corresponding to any value of argument within the range. This is interpolation. And extrapolation outside the range. This is a process of estimation of the value of y, value of the function corresponding to the given or whatever value is given to argument outside its range, outside its range. So outside is also this range, outside is also here in this direction is outside, in this direction is the outside. But remember, while making the extrapolation through or by the Newton's forward interpolation formula, you can extrapolate little bit backward, little bit left, you can say, backward of initial value. Means initial value is this. If you put here y1, then initial value is y1. So here somewhere one term or two terms backward you can apply for the extrapolation. Similarly here, in case of interpolation, here is the y1, here is the y2, and around y1, y2 you can interpolate. Not you are coming to, suppose there are 5 terms, then 5 terms y0, y1, y2, y3, y4, y5, that's all. So near y4 and y5 you cannot interpolate. In the beginning you can extrapolate, in the beginning, around the beginning you can interpolate. So whatever initial value is, around that interpolation and extrapolation both are allowed with the help of the Newton's interpolation formula. So Newton's interpolation formula is very useful, but it has its own restrictions which we have to keep in the mind. Now this theory is okay. Tomorrow I'll discuss the numerical, and after discussing the numerical, this topic will be clear. Now the further topics may be the backward interpolation formula and others. Now basics are clear, so I think other things will be very easy for discussion. So thank you very much for this lecture, and we will meet you again tomorrow. If you have any query, you can ask.